Hello class. In this lesson we will explore Lewis structures of molecules in addition to draw Lewis structures of molecules based on common bonding patterns. So first, let's take a look at some notation and make some inferences about how we are going to represent electrons in our Lewis structures. I have four terms here: single bond, double bond, triple bond, and a lone pair. And that is paired with a series of images on the right side here. I see that three of the images consist of lines, so I have a single line, I have two lines, and three lines. I can make a pretty good bet that letter D represents a single bond. If one line is a single bond, I can bet that letter B, two lines, is a double bond. Three lines would be a triple bond. And then I have this new term called a lone pair. A lone pair is represented by two dots. So we have to think about what these bonds represent. As I mentioned, they represent electrons, but how many electrons do they represent? Well, whenever we form a covalent bond, we are going to share a valence electron that the atom currently has with another atom that is also going to share a valence electron. Since each atom is sharing a valence electron, one covalent bond represents the sharing of two electrons being shared. If one line represents two electrons, then two lines is four electrons being shared, and three lines is six electrons in total being shared. Key idea is that we have two electrons per line. The next thing we can look at is the relationship between the valence electrons and the number of bonds typically formed and the typical number of lone pairs. Before we do that, we need to apply what is called the octet rule. We know from ionic bonding that atoms will form ionic bonds by gaining or losing electrons so that they have a full valence shell, which is usually 8 electrons. Since we aren't showing the transfer or gaining or losing of electrons in a covalent bond, but rather are showing the sharing of electrons in a covalent bond, we need to figure out how many more electrons does a particular atom need in order to complete its octet. So I have outlined how many electrons each of the atoms in the example have, and I need to figure out how many more does it need to get to 8. Well, if carbon started with 4 electrons, it needs 4 more to have a complete octet. Nitrogen has 5 valence, so it needs 3 more electrons to complete its octet. Oxygen has 6, so it needs 2 more electrons to complete its octet. The halogens have 7, and I hope you figured out this pattern by now. It needs 1 more electron to complete its octet. I included hydrogen here because hydrogen's a special one. We'll discuss the reason why in a little bit, but hydrogen can only have 2 electrons in its valence shell. So even though I'm going to use the word octet here, a full valence shell for hydrogen is not going to be 8 electrons, but it's going to be 2 electrons. So hydrogen has 1 valence electron already. It needs 1 more to complete its valence shell for a total of 2 valence electrons. Now let's take a look at each of the atoms in the molecules given above and figure out how many bonds those atoms form typically. So I have a carbon here, carbon, carbon, and carbon. For the carbon on the left, I see that there are 4 lines, so there are 4 bonds. Let's check that with the other atoms. I see 1, 2, 3, 4 lines on this carbon. Change my color here for the next one. 1, 2, 3, 4 lines, so we're still consistent there. Ooh, what about this last one? 1, 2, 3, 4 lines. Interesting. So carbon in this last example still has 4 lines, but 2 of them are single bonds and 1 of them is a double bond, whereas in the other molecules, they're all single bonds. We'll get into that more later, but we can keep this answer the same. We know that carbon typically forms 4 bonds. Let's take a look at nitrogen. I'm going to pick a different color, let's say blue. I only have 1 nitrogen here. It's got 1, 2, 3 bonds. Okay, let's take a look at oxygen. Oxygen here has 2 bonds. If I check the oxygen on the right, it has 1 double bond, but that still has 2 lines. So we can also think of that as 2 bonds. I'm beginning to notice a pattern here. It seems like the number of electrons needed to complete the octet is consistent with the number of bonds that the atom typically forms in a covalent bond. So I can take a look at my halogens. I see bromine. Bromine has 1 bond. I see each of these chlorines also has 1 bond. So the halogens need 1 more electron to complete their octet, so they share one of their 7 valence electrons with another atom that also shares one of its valence electrons to make 1 covalent bond. If we take a look at hydrogen, each hydrogen also shares 2 electrons to form 1 additional bond. The next thing we can look at here, next thing we can look at are the number of lone pair electrons. So lone pair electrons are all these fancy little dots that exists in groups of 2. So remember, a pair is 2. If we look at carbon, none of the carbon atoms tend to have lone pairs. They seem to have only lines. For nitrogen, I see 2 electrons. Oh, that's a common mistake. Yes, there's 2 electrons, but that's only 1 pair. So we got to make sure we're applying our language there. All right, let's take a look at oxygen. Oxygen has 4 electrons, but if we think of it in terms of pair, that is 2 pair. And then the halogens have 6 electrons, or 3 pair. So let's take a moment and think about this. What do you notice about the relationship between the number of bonds typically formed and the typical number of lone pairs? Well, each of these add up to a total of 4. If we think about that, if we have 4 pairs times 2 electrons per pair, that will always give us 8 electrons. It's the goal of each atom to have 8 electrons due to the octet rule. Again, the one exception to that is going to be our friend hydrogen, because it has a different kind of bonding arrangement. Notice that none of the hydrogens have lone pairs. Hydrogen will never, ever, ever have lone pairs in a Lewis structure. It will only have 1 single bond. Let's take a look at why. To figure out why hydrogen only has 2 valence electrons in its valence shell, we have to think back to electron configurations and orbital notation. Here, I'm going to represent the orbitals as boxes, and I have the 1s orbital, I have the 2s orbital, and slightly higher in energy is the 2p orbital. Now, I know that the orbitals can go up into much higher energy levels, but we're just looking at the first 2 rows of the periodic table at the moment to help us come up with our patterns. How many electrons can we put in each orbital? If you recall, you can have 1 up arrow and 1 down arrow representing 2 electrons in total. If we were to complete our orbitals, remember in the 2p level we spread them out and then we compare. I can take a look at the number of electrons in each energy level. Remember, the first number is the energy level. So how many total electrons do we have in the second energy level? Well, you have 2 from the s orbital and 6 from the p orbital, which makes 8. Hey, that matches up with our octet rule. That's pretty cool. What about the first energy level? Well, the first energy level does not have any p orbitals, so we max out at 2. Remember, hydrogen is in that first energy level, along with helium. Because hydrogen and helium are in that first energy level, their valence shell is full once it has 2 electrons. So that is why hydrogen is special. It can never have more than 2 electrons because there's no p orbitals for those electrons to go to. I figured it was worth bringing this back up because this will help us understand bonding a bit more later on down the line. Okay, let's evaluate some central atoms. Recall the periodic trend of electronegativity. This is the ability of an atom to attract electrons towards itself. We're going to look at the central atoms in each of these structures, so C and N, and we're going to compare their electronegativities. If you go on the periodic table from ptable.com, you can highlight a particular atom, and over here in the left side, it tells you the electronegativity. So carbon is 2.55, oxygen is 3.44. Let's make note of those. 2.55, 3.44. And then the other atoms here, I need to look at nitrogen, bromine, and hydrogen. Bromine is 2.96, nitrogen is 3.04, and 2.20 for hydrogen. So 2.20, 3.04, and 2.96. All right, if we compare the central atom's electronegativity value to the numbers of the other atoms it's bonded to, we see a general pattern here. Hydrogen's going to deviate from that pattern, and we know hydrogen is special, so I'm actually going to ignore hydrogen's electronegativity here. But if I look at the other values, I see that the central atom has a lower electronegativity than the atoms it's bonded to. So central atoms typically have less electronegative atoms than the atoms they are bonded to. Again, I use that word typically. What we're looking at here is a series of common bonding patterns. These common bonding patterns hold true most of the time, but sometimes we can deviate from a pattern. Next, we can look at elements with expanded octets. If we take a look at these structures, it says the compounds above feature central atoms that have expanded octets. Based on the structures, describe what you think an expanded octet is. Well, I notice that I've got 5 bonds on phosphorus. 5 times 2 is 10 electrons. That's interesting. I've got 6 bonds, on sulfur times 2 electrons each. That's 12 electrons. This chlorine has 3 double bonds, which is actually 6 bonds in total, and a 7th bond. So 7 times 2 electrons is 14 electrons. And I can continue looking at all of these, and I see that the number of electrons is much greater than 8 each time. It's not a consistent number from one structure to another, but an expanded octet just means we can have greater than 8 electrons on the central atom. Okay, so now we can take a look at the locations of those elements on the periodic table: phosphorus, sulfur, chlorine, bromine, and iodine. Phosphorus, sulfur, chlorine, bromine, and iodine. Notice that they are in the 3rd, 4th, and 5th rows of the periodic table. The rows are called your periods. This is period 3, 4, and 5. So atoms in the third period and below appear to have the ability to have expanded octets. We also have some compounds here, beryllium, boron, and aluminum. These compounds are exceptions to the typical rules for Lewis structures. Let's think about what appears to be incorrect about these. Well, if I look at aluminum, it's got 3 bonds times 2 electrons. That's only 6 electrons. Boron has the same thing, only 6 electrons. And beryllium has 2 bonds times 2 electrons. That only has 4 electrons total. All of these are referred to as atoms with an incomplete octet, or less than 8 valence electrons. So our central atoms, for the most part, are always going to follow the octet rule, but there are a few exceptions where sometimes it can be greater than and sometimes it can be less than. Remember, these patterns are a rule of thumb. It is not a tried and true thing every single time. So if we stick with our main patterns, that's going to help us to generate our Lewis structures most of the time. And there are a couple of ones we just have to be on the lookout for in the event that we encounter them. So as a quick review, we said elements in the third row and below: phosphorus, sulfur, chlorine, bromine, and iodine. You can also make a case for any of the other nonmetals that far down. If you said selenium, for instance, I'd be willing to accept that answer. Which atoms can have less than 8 valence electrons? We have beryllium, boron, and aluminum. Now, think about beryllium. Beryllium's group 2, which we think is actually a metal. Beryllium is a low electronegativity, so even though it's a metal, it can actually form covalent bonds on occasion. That's interesting. Boron and aluminum are elements that are in that metalloid and post-transition metal area, so they're not quite nonmetals, but they're not quite tried and true metals either. So that is something to keep in mind. All right, let's do a quick recap on some notes, and then in the next video we'll get into how to actually draw some of these Lewis structures. So in summary, in a covalent bond, electrons are shared so that all atoms have a full valence shell. Typically that means a complete octet or 8 electrons, but as we saw with hydrogen and helium, it's only 2 electrons because those two particular elements don't have a p orbital with which to hold more electrons. The central atom is the atom that tends to gain the most electrons. Generally, it's the least electronegative. A bonding pair refers to a pair of electrons that are shared and typically represented with a line. A lone pair of electrons is a pair that is unshared and is represented as 2 dots that are next to each other. As we explored in our exploration above, the number of bonds an atom forms is generally based on how many valence electrons the atom needs to complete its octet. For instance, atoms with 4 valence electrons will form 4 bonds because it needs 4 more electrons to complete the octet. An atom with 5 valence electrons will form 3 bonds because it needs 3 more electrons to complete its octet. Any electron that is not participating in sharing is going to be a lone pair on that atom. Let's see if we can highlight that again. So for instance, oxygen has 6 valence electrons. It needs 2 more to have 8 total, so it will form 2 bonds. 4 of the electrons will be participating in bonds. The other 4 electrons will be participating in lone pairs. So if we think about that for a minute, oxygen has 6 valence electrons. 2 of them are going to be pairs, and the other 2 are going to be participating in some sharing. So oxygen will share 2 of its valence electrons with 2 other atoms, and those other atoms will in return also share a valence electron. So that way oxygen ends up with its full 8 valence. As I mentioned, there are scenarios where this is not always true, but this serves as a good rule of thumb. Here's a good little summarizing chart that represents how many electrons are shared for each bond type, how many lines that represents, And then something that we'll look at later on in the unit is this impacts bond strength and bond length. Typically, the more electrons that are shared, the stronger the bond. Also, the more electrons shared, the shorter the bond. The fewer electrons that are shared, the weaker the bond, and also the longest, or the longer the bond. All right, in our next lesson, we will get into actually how to apply our common bonding patterns to draw our Lewis structure.